If you are not familiar with solving such kind of problems, it will seem like a difficult problem. Therefore, it is important that you become familiar. Let us start. Let me give you a brief description of the problem. The setup is shown in the figure. The floor has a friction with coefficient of static friction mu. The wall is smooth and therefore no friction. The angle of the ladder with respect to floor and the length of the ladder is given, which is theta and L. The distance of the person along the bottom of the ladder is given, which is A. You are asked to find the force the wall is going to exert and the maximum distance of A before the ladder starts slipping along the floor. You may pause the video if you like to read the problem and think. Let me continue with solving the problem. Let us define the contact points of the ladder, A on the floor and B on the wall. Let's bring the forces one by one that will be shown in red arrow. First, the weight of the ladder at center of mass of the ladder. Then the weight of the person. Now since the wall is smooth, there is no vertical force. Since the system is static, that is, it is not moving up or down, so the normal force at the point will respond in such a way to balance all the downward forces, and therefore the normal force will be equal to the weight of the ladder and weight of the person. Hope it is clear so far. Now let us discuss about horizontal forces. The bottom of the ladder wants to move to the right, but the friction force will prevent it. Again, the system is static. There is no net force horizontally. Therefore, the force from the wall will counteract the force of friction so as to make the net force as zero. Actually, the force from the wall is a normal force. Normal force just means force perpendicular to surface. Now we have all the forces that are in play. It is time to move to the next level and discuss about torques. Torque is, roughly speaking, a tendency to rotate. Since the system is static and not rotating, the torque at any point is zero. We choose that any point cleverly as point 8 to calculate the torque. This is because it will remove the contribution of normal and friction force because the distance is zero. Now let us draw the position vector. Now let us use our common sense to see how the individual torque will act or when they balance. So let us go ahead and calculate the torque from the ladder. As you can see, it will try to move downward. Let us see the torque from the person. This will also try to rotate in a downward direction. Now let us see the torque from the wall. Aha! That will move in opposite direction and try to balance the ladder. Great! We seem to be in the right direction. Now let us try to calculate exact expressions. Let us take a deep breath before I give you high dose of physics in a short time. Now let us calculate the torque from the individual forces. We draw all the vectors separately for clarity. We draw the position vector, check if it is parallel to the original position vector. Yes, it is. We draw the horizontal and the angle happens to be the same. Now we check for the force from the ladder as well as a person. It is downwards and perpendicular to the surface. Now the torque is R cross the force. So we go from R to F. It is out of the page and therefore positive. The actual torque will be given as the magnitude of the position vector times force times sine of the angle in between. The angle in between is 90 plus theta. From the mathematics, we know sine 90 plus theta equals to cos theta. So we get a simple expression. Now we do the same thing for the person. It is exactly the same. The only difference is the magnitude of the position vector, which is A. And we get this as the torque from the person. Now we find the torque from the force of wall. The force from wall is horizontal and to the right. The angle from the position vector is 180 minus theta. Let us now find the direction of torque. Since the torque is R cross force, we go from position vector R to force of wall in clockwise direction, which is into the page and therefore negative. The expression of the torque is this, which is magnitude of position vector, which is the length of the entire ladder, times the force of wall times the sine of angle in between, which is 180 minus theta. Sine of 180 minus theta is sine of theta, and we get a simple expression. Now all the torque combined gives 0 because the system is static and there is no rotation. This gives the following equation, which with a bit of algebra gives force of wall. And that is the final answer to the first part of question. In this slide, we rewrite the force of wall that we got previously. As you can note, the right hand side is all positive. So when A increases, which means person climbs the ladder, the force on the wall increases. As noted earlier in the video, the force of wall is same as force of friction at the bottom of the ladder. We know during the study of friction that the maximum force of friction is coefficient of static friction times the normal force. Now we know the maximum force of the wall, and we get the following equation from which we can get A max, which is the final answer to the second part of the question. Here we summarize the answers in the final slide. You may have some lingering questions, such as how did we go from position vector to the force which was inside the page and negative. It is really a recipe to remember the way of finding the direction of torque, and it is described in a different video. We have the link provided in the description in case if you like to know. That is all for now. Bye bye.